making good progress. And I think the way, some of you will be following this with great enthusiasm because it's cool. You're weird like me. And some of you might be feeling slightly nauseated by now. And for those of you like that, I think the thing to remember is I'm going over a fair amount of complexity here to be complete and show you how every little bit works. At a functional level, like at the level of a statistical user, which you will be, really the only things you need to know about are the procedural things. How to actually run the model, how to generate a prediction, how to understand the values of these coefficients. Does it make the odds better or worse? By how much? That kind of thing. So do your best to follow the fine-grained trail of breadcrumbs here. But if you start zoning out, it's okay. I'm not going to ask you those detailed questions on an exam. It's going to be much more high level. Okay, we just talked about how to interpret these coefficients on each independent variable. And we talked about it in terms of an odds ratio. An odds ratio greater than 1 implies a positive association, and an odds ratio less than 1, like what we have here. So you take e to the power of that, and you get the odds ratio. And an odds ratio less than 1 means a decrease in the outcome. Yeah?
If we were to do this with like multivariate regression, would there just be like, would we just apply this to the other formula? Like, would it and then just be e to the beta 0 plus beta 1 x1 plus beta 2.
Yeah, so the question is if we have multiple x variables, not just age. Is it a question of how to interpret the slopes or how to generate the prediction? Okay, yeah, so to generate the prediction, yeah, we would do exactly what you said. We would just run it through the whole thing. Probability equals e to the power of beta 0 plus beta 1x1 plus beta 2x2 plus beta 3x3 divided by 1 plus e to the power of beta 0 plus beta 1x1, beta 2x2, and so forth. That would generate the predicted value for a given x1, x2, x3. To interpret the slopes on each x variable, it's just like this. We would interpret each slope in isolation, basically. We would say, let's say we had age and sex and marital status as 3 variables, and we wanted to assess the coefficient on age, we would say, what's the effect on the outcome of a unit change in age if the other things are held constant? And if we wanted to assess the slope on marital status, we would say, what's the effect of outcome based on marital status if age and sex were held constant? So we wouldn't vary more than one thing at once.
So if we were to do that with, let's say we had 2 predictor variables.
2 predictor variables.
So like how in bivariate regression it would be a plane.
Yeah.
How would that look like with a sigma?
Yeah, so the question was, in bivariate linear or in multiple regression, like last week, we had 2 predictor variables, x1 and x2, predicting y. The model can be visualized as a plane in 3D space going through the cloud points. If we had 2 predictor variables for logistic regression, what would it be? It wouldn't be a plane anymore. How would we visualize that? What do you think it would be? We know what one variable looks like. It's a sigmoidal curve. If we had another sigmoidal curve in an orthogonal direction, what would that look like? Any people with graphically minded minds? Budding architects? I'm not good enough to draw. I can't draw to save my life, but I think, I'm not even going to try. How to think about it. Imagine a swimming pool, right, with a shallow end. So a swimming pool that's a square shape, okay? And in one corner of the square is the shallow end. And in the other corner, the opposite corner, is a deep end. And the steepness, if you look on this side of the pool or on that side of the pool, the steepness goes down sigmoidally. So that means in the shallow end it will be shallow, and then it kind of drops off in both directions gradually to a deep end. Maybe? Kind of get me? Yeah. So it wouldn't be a plane, it would be a curvilinear, a nonlinear surface that's sigmoidally shaped in two different directions, basically. Now the sigmoids don't have just the same shape. One could be really shallow, one could be really steep. But it would basically be what I just said. Does that make sense? Okay. I don't want to go over this. I think we've talked about odds enough. And yeah, ignore that. Let's go right to predictors. So if we have two predictors, for example, age and sex, it could be male or female in this data set. To fit the model, it's just like multiple regression. We would say age plus sex. The plus just tells us that we want to add another variable as a predictor variable. And everything else is the same. And when we fit that model and we ask for the coefficients, now we get 3. We still get an intercept, which we're not really interested in. Then we get a coefficient on age and a coefficient on sex. And R doesn't just report sex, which is the name of the column. It says sex female. And so it chooses alphabetically the first one, which is female. The second one will be male. And we'll talk about what that means in a sec. If you plot this graphically, you can look at it like that. But the equation now looks like this. Log p over 1 minus p equals our intercept minus the coefficient on age plus the coefficient on sex. Or if you express it in terms of p, probability of survival equals e to the power of beta 0 plus beta 1 age plus beta 2 sex over 1 plus e to the power of beta 0 plus beta 1 age plus beta 2 sex. Just like before, we just added another beta and another x variable. So the coefficient for R calls it sex female is 1.5. What this means is that R coded males as 0 and females as 1. Because sex in the data frame is categorical, it's not a continuous variable. It's male and female. R decided to code them as 0 and 1 for the purpose of this model. And so the model for males looks like this. Log p over 1 minus p is beta 0 plus beta 1 times age plus beta 2 times 0. And the model for females is the same except plus 1.5 times 1. So if it's males, it's this value of x is 0, and if it's females, the value is 1. So when R says sex female, that's R trying to tell you, by the way, I modeled this categorical variable as female is 1 and males is 0. Okay? So that's one little wrinkle when you use a categorical variable, is R will recode it as 0 or 1. And if it was 3 categories, we won't look at it, but you would have, I forget what you would have. Is it 0, 1, or 2, or is it minus 1, 0, plus 1? I forget. R does something like that, but we don't need to talk about that today. So that's how it codes the sex variable, and now you've got 2 coefficients, one for each x variable. So let's talk about them. The coefficient for age now is 0 minus 0. We'll call it 0.9. If we take e to the power of that, we get 0.91 for our odds ratio of survival. So that means plus 1 unit of age corresponds to a 0.91 odds ratio of survival. Is that better or worse? If you add 1 to age, does odds of survival get better or worse? Yeah, worse, because 0.91 is less than 1. If the odds ratio of survival was 1.0, that means it would be the same probability of survival if you're 1 year older or not. If it's greater than 0, that means the probability of survival for 1 year older would be higher than without 1 year of age. And if it's less than 1, it means the survival goes down with an increase in age. What about for the sex predictor variable? So the coefficient for sex female is 1.5. That means that for females, the log odds of survival increases by 1.5 over males. Or equivalently, we take e to the power of 1.5. The odds ratio of survival is 4.5. So don't look at that bottom stuff just yet. The odds ratio is 4.5. That's way higher than 1, right? So that means the odds of survival for a female of the same age as a male is hugely more in this data set than if the person was male. So way, way, way above 1. We don't have to go through that. That was me trying to show you step by step how this formula can end up with a 4.5. But we don't need to do that now. Let's talk about model fit. So just like multiple regression, where we refine the model, where we use the step procedure to ask the question, what should stay in the model, what should go? We can do the same kind of thing with logistic regression. And remember I said earlier in the class that when you produce the summary of the model, you get AIC at the very bottom. This measure it's a measure that trades off model fit and model complexity. And a lower AIC is better. So we can fit a model that only has age, and we get an AIC of 57.134. We can refit a model that has age plus sex, and look at the AIC, and it goes down. That means this is a better model, even taking into consideration that it has an extra parameter. Right? In general, when you add a parameter to a model, you're always going to get a better fit. The model's always going to fit the data better. Always. It's sort of a mathematical certainty. Unless the thing you add is literally identical to some other thing that was already there, in which case the fit won't change. Even if you add random numbers as a predictor, your model fit will get better. You can try it. So the more things you add to the model, the better it will fit. But really the question we want to answer is, does the increase in fit, is the increase in fit worth having to estimate another parameter? And that's what AIC will tell you. So AIC goes down when sex is added to the model, so we wouldn't keep it in the model. Yeah, AIC is lower, that means better. Better fit even considering the extra parameter we have to estimate. So you can do it kind of by hand like that, but you can also use the step function. Just like we did for multiple regression last week, you can use the step function to automatically do all of this stepwise removal and addition to the models. And R will do it for you and spit out all the steps along the way, and then the final model it comes up with. So that part is the same as last week. Once you use GLM to estimate your model, you can use the step function exactly the same way as last week. So let's talk about the assumptions of logistic regression. It doesn't require an assumption of linearity, obviously, because we're not estimating a linear model anymore. So we don't have to worry about that. It does require, though, that the predictors are linearly related to the log odds of the outcome. Why? Why is that? Well, if you look at the equation, we have a linear equation here on the right, and that is equal to the log of something. Remember when we defined the odds of something? It's the probability of one outcome divided by the probability of the other outcome. That's what P over 1 minus P is. So this is the log odds. Log P over 1 minus P is the log odds of the outcome. And that is a linear function in our model. So the probability of success isn't linear in this kind of modeling, but the log odds is supposed to be linear. And there's a way to test for that, as we'll see. Another assumption, it does not require normality of the residuals, but it does require that they're independent of each other. And just like for multiple regression, there's no numerical test of whether the observations are independent. That's something that you just have to know sort of from first principles when you collect your data. If you collect your data from roommates in the same apartment, they're probably not as independent as if you collect them from complete random strangers across the whole city. It's that kind of thing. It does not require homoscedasticity. It does require, obviously, that the dependent variable is binary for logistic regression. And again, this is just something we know from first principles. And like multiple regression, it does require that the predictor variables are independent from each other. So collinearity is still something to check for, even in logistic regression. And as we saw last time, you can test for that. Anyone remember what the name of the metric that we can use to assess collinearity? It was something from the Navarro book that I just mentioned in the slide but didn't really describe. What's the name of the metric we use to look for collinearity? Yeah? Yeah, that's it. Good. Variance inflation factor, VIF. So go look at that. Okay, another thing we have to worry about in logistic regression is how much data we have, because it's pretty sensitive to that, actually. It typically requires a pretty large sample size to provide a stable model fit. And a rough kind of back-of-the-hand guide is 10 cases minimum, considering the least frequent outcome for each predictor variable. So for example, if we have 3 predictor variables, and the probability of the least frequent outcome is around 0.3, the sample size should be 10 times 3 over 0.3 is 100. That's just a really rough kind of back-of-the-hand calculation about how much data you should have. But the bottom line is, logistic regression, unfortunately, is a bit more sensitive to having enough data. What happens if you don't have enough data, basically, is that really tiny changes in the value of any one observation can radically change the shape of that sigmoidal fit. And you can kind of understand, right? An individual observation in a logistic regression is either 1 or 0, right? It's success or failure. There's nothing in between. In a regular linear multiple regression, where values can take on any value, when there's variability in the data, the data points can kind of dance around up or down a little bit. With a binary outcome, if there's variability in an outcome, it suddenly goes kaplunk, right? 1, 0, 1, 0. And so if you don't have very many data points, and you're fitting the sigmoid, and one of those data points suddenly completely changes to the opposite scenario, that can radically change the shape of the function. So the solution is to have a lot of data points, so that if any one or any small number are highly unreliable, then them changing from a 1 to 0 or vice versa won't radically change the shape of the function. Okay, so we're going to look at one of the things I said that we do have to check for, not the linearity assumption like in linear regression, but linearity in the log odds of the outcome. And there is a way to check for that. Are the predictors linearly related to the log odds of the outcome? Not the probability of the outcome, but the log odds of the outcome. And so what we're going to do is we're going to take the data like this, and we're going to slice it up into bins. And we're going to slice it into bins using the quantile function. So the quantile function will basically, like if we ask for four quantiles, it's going to start counting data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And once we get to a quarter of the data, it will define a boundary. And then we'll count until we get the next quarter of the data, and it'll draw a line. And then the next quarter of the data, and then the next quarter of the data. So each bin, each of these 4 bins has a quarter, 25% of the total data in it. And within each of those bins, we're going to compute the probability of the outcome of success, P. And then once we have P, we can compute the log odds by taking log of P over 1 minus P. So that's what I do here in this sort of dplyr sequence. I take our data set, Donner, and I mutate probability equals, if else, status equal survive 1, 0. So I'm just recoding our our status variable as a 1 or a 0. Because in the original data set it's called, I don't remember what it's called, survived and died. I'm just recoding it as a 1 or a 0. I pipe that into another mutate where I define age bin equals cut. And I'm cutting age, I'm slicing up age. And what breaks am I using to slice it up? Quantile of age. The quantile function by default gives you the 25% quantiles. You can ask for the 20% quantiles and get 5 bins, or the 10% quantiles and get 10 bins, whatever you want. The default is the 25% quantiles, so we get 4 bins. Include.lowest equals true. I don't remember what that means. That's Don's true. Then we group by age bin, and we summarize the number of observations in each bin, the mean in each bin of age, the mean probability, and then we compute log odds. Log of bin probability over 1 minus bin probability. And the result of all that is this. We get 4 bins, 1, 2, 3, 4, 1, 2, 3, 4. And for each bin, we see how many observations in each bin, roughly 25%. We see the average age in each bin. Importantly, we get the probability of survival in each bin. So you can see it's really high, 0.7 for the lowest bin, and it's really low for the highest bin, for the oldies. And then the log odds is just log of P over 1 minus P. So log of 0.727 over 1 minus 0.727 is equal to 0.981. So why are we doing all this? Because we want to get log odds as a function of age. We can't get that from the raw unbinned data, because the raw unbinned data are just single points that are either 1 or 0. There's no P, there's no probability there. It's either 1 or 0. So by binning the data, we can compute an average probability within that bin. So that's why we're doing it. So we get log odds as a function of age. And we're doing that because the assumption we want to test is that the predictors, like age, are linearly related to the log odds of the outcome. So now if we plot mean age in each bin against the log odds, of each bin, we can make an assessment. Does it look linear or not? So here's what that looks like. Age, the mean age of each of our 4 bins, 1, 2, 3, 4, and the log odds of survival in each bin. Do they fit along a straight line? Kind of. Maybe? I'm not sure. Sort of. They kind of go down. But it kind of goes down and up and down. In this data set, there isn't very much data. It's a bit of a toy data set. So I wouldn't put too much stock in that kind of plot. But you'll see an example in this week's lab, in the homeworks, of a much bigger data set, where this kind of plot very clearly shows a linear relationship between the predictor variable and the log odds of the outcome. So that was kind of a long-winded thing, but the bottom line is there is an assumption of linearity. It's not linearity in the dependent variable. It's linearity in the log odds outcome of the dependent variable. And you still have to check for that. And you can check for that by doing this kind of plot. There's also a quantitative test for linearity in the log odds of the outcome. It's called the Box-Tidwell test. And it tests for whether there's an interaction between the predictor and the log odds of the outcome. If there's an interaction between them, it means that the relationship between them is different at different values of x. We're going to talk about interaction effects more in a couple of weeks when we talk about the factorial ANOVA. So don't worry too much about it now. But the general idea is it's testing whether the relationship between x and y is the same across all values of x. Think about what that means. If the way that y changes when x changes is the same across all values of x, I'll say it again. If the way that y changes when x changes is the same across all values of x, that must mean it's a straight line, right? The way that y changes when x changes is the slope. So if the slope is the same for all values of x, that means it's a straight line. If the slope is different for different values of x, that means that the line is not linear. It changes slope. So that's what this tests for. It tests whether the slope is constant or not. If the test is significant, then that's bad news. That means the relationship between the predictor and the log odds of the outcome is not linear, and you violated that assumption. So I won't go over it right now, but in the slides it shows you how to run that Box-Tidwell test. You also have to check for outliers. And just like before, we can use Cook's distance observations with a high value of Cook's distance or outliers. And in general, values above 1 are considered high. Here's the Cook's distance data for our Donner Party data set. They're all very small, way below 1, so we don't have to worry about outliers. Collinearity, just like last week, we can visualize it using GG pairs, and we can test for it using various inflation factors. Read the chapters for more details about that. But the same principles apply for logistic regression as they do in multiple regression. Okay, so the bottom line tests you have to do for assumptions in logistic regression. Collinearity, outliers, the linearity of the predictor variables in the log odds of the outcome, and what else? Anything else? Forgot. I don't remember right. I think that's it. Sample size. Yes, but the sample size is big enough. Yeah, thank you. Okay, thank you.